All right, just like we split lesson 1 into 2 parts, we're also going to split lesson 2 into 2 parts just to have some bite-sized chunks for us to wrestle with. Again, these are things that we're trying to incorporate into our Algebra 1, so it's going to take us a while to kind of get through kind of reviewing this content and making sure that we're feeling comfortable with transforming our functions. But this will set a good groundwork for you to be able to anticipate what your graphs of your functions will look like before having to type them in your grapher. That's kind of the whole point of this, so that you can be graphical thinkers and not just relying entirely on the calculator or on your ability to make an XY table, etc. So there are some key vocabulary terms that we'll explore, but the big thing is that you're able to apply transformations to functions so that you can write equations and make graphs. That's really the whole point of this lesson. And we're going to start with this idea of parent functions. The parent function is sort of the most basic version of a family of functions. So we have linear functions that are just y equals x, but then we have different versions of that, like y equals mx plus b. And then here we have a parabola, and I'm showing different ones that are maybe a little more narrow, a little wider, they're stretched out a little taller, the vertex is moved, some are upside down, opening downward, some are opening upward. And so what we're talking about with parent functions is just kind of the most basic version of a parabola is y equals x squared. And so let's kind of talk through each of those types of functions. So parent function is the function y equals x. The domain is all reals. All reals for the range. It is increasing from negative infinity up to positive infinity. It's decreasing nowhere. X-intercept is at 0, 0. The y-intercept is at 0, 0. All right? And so we have this understanding of what a linear graph is going to look like. And then if we were to just move this up, it doesn't really change too much there. It'll probably just change the intercepts, right? It maybe gets tweaked a little bit, and maybe there's a slope added, so it's a little steeper. It's going up, it's going down, whatever. It might change how it's increasing or where it's decreasing. It might change the intercept. But overall, it's going to maintain the same domain and range, right? That's generally what will happen with a linear graph. X squared. For y equals x squared, we have a parabola, and we know that the domain is all real numbers, so the domain is from negative infinity to positive infinity. The range is from the vertex on up. In this case, it's from 0 up to infinity. It's going to be increasing from 0 to positive infinity, but it's decreasing from negative infinity to 0. All right, remember, non-inclusive on that because this is the part of the graph where it's decreasing, it's going down. All right, the x-intercept and the y-intercept, same spot, 0, 0. That's where it starts, and we kind of build our graph out from there. Next up, we're going to look at absolute value functions. And so there's the picture for our absolute value parent function, and this is where we have y equals the absolute value of x. Again, your domain here is, oh my gosh, this marker's terrible too. I just replaced the marker. That's why I paused the video. Did it work? No. Ah. All right, I got it to work. Our domain is all the x values, right? We can put any number in for x from negative infinity to positive infinity. Our range, however, goes from 0 inclusive up to positive infinity on this basic parent function. Y is the absolute value of x, right? So the range goes from the vertex on up. It is increasing from x equals 0 to x is infinity. It's decreasing from negative infinity to 0, right? Here it's going down to this point, and then it's going up from that point as we read it left to right. X-intercept and y-intercept are the same, 0, 0. All right, so we've seen a lot of similarities from function to function to make sure that we can think about these lines, these parabolas, these absolute value graphs. When we have a constant, y is just equal to a number, our domain is just that number, right? Our range is just y equals 1. Increasing, never. Decreasing, never, right? The slope is 0. There is no x-intercept, but on this there is a y-intercept at y equals 1, so we have the point 0, 1. All right? And your constant graph, you can move that up or down. All right? If you are talking about a vertical line, that is not a function, and so we won't have to worry about that for this part of the conversation. All right. Now, This is your blanket rule for all transformations. All right, this is your blanket rule for all transformations. Given a function, we can describe how the graph moves, left or right, up or down, by subtracting from the x and by adding at the end of the function. Okay, so it's kind of a neat trick, but this is kind of our reminder for all of our linear graphs, for all of our parabolas, all of our absolute values, et cetera, et cetera. This is going to be a very useful setup for our translation. So here we have the graph of the parent function y equals x squared. But then when I have y equals x minus 2 squared, I'm moving that 2 spaces to the right. So moving to the right, you are subtracting, moves right h spaces. Now that seems a little bit backwards, right? Because you are subtracting, so you think you're going to go to the left, but you're actually going forward. It's okay if it feels backwards, just know that it's not. All right, so if you need to make a flashcard to help you remember, that's great. But basically what we're doing is we're going to take this, and if we're subtracting 2, it would take us back to the 0. So that's how we know that this moves us to the right. If we are adding, then we are going to be going to the left h spaces. All right, so here's the absolute value of x in red. In blue is the absolute value of x plus 1. We're shifting that, that vertex to one spot to the left. One spot to the left. Up is when we add on the outside of these parentheses. We'll take the absolute value, or we'll take the function of x, or the absolute value of x, or the parabola x squared, and we'll move it up k spaces. All right, up k spaces on the y. Right, this is going to change the y, whereas the other one changes the x. So we're going to take this. If this is y equals x, and this is y equals x plus 3, we're going to go up 1, 2, 3 steps. And then finally, down. When we have a subtracting k, that means we're going to move down k spaces. So y equals x cubed looks like this. I know that you maybe haven't seen cubics before, but this is what y equals x cubed looks like. Negative times negative times negative is going to be more negative. Positive times positive times positive is going to be more positive. If I take this graph and I subtract 4, I'm going to have the same picture. It's just going to be moved down 4 spaces. 1, 2, 3, 4. And you can just count them. So if you know your x comma y's for your original graph, then you can predict what that's going to look like. You can even count out what it's going to look like so that you can draw the graph easily, quickly, without having to type in your grapher calculator, or if you don't have access to your grapher, all right, on like a non-grapher part of an exam or something like that. So given the parent function f of x, describe what happens when you write g of x. So what I'm going to talk about here is this is on the outside, this is up 7. All right, this is x, absolute value of x plus k, and that's a positive k, so that's going to go up. Over here, this is a minus 1, but in the middle with the x, before we square it, that means that we're going to go right, not left. I know that feels backwards, but we're going to go right 1 space. Spaces. All right, here we've got 2 things happening. We've got something happening inside, that's a left 3. And we have something happening on the outside that's a down 2. So we're going to go left 3, and then we're going to go down 2. Can you do this one? You do letter D for me. Tell me where we're going to move. Left or right, up or down? A little bit of both? How's that going to go? Writing the equation. Knowing what the translation is, can we write the equation that translates this 3 units to the left? Left is backwards. So we're still going to have g of x here is equal to something to the 4th power. Am I going to add 3 or subtract 3? We are going to add 3. I know that we're going left, and we want to think that that's negative, but the way to make that make sense is it's going to be in the opposite direction, all right? So we're going to add 3 is going to move us left, because we're going to take that picture of y equals x to the 4th, and we're going to move it to the right. For letter B, we want to translate to the right 7 spaces and up 7 spaces. So this is going to be inside, and this up 11 is going to be outside. The way we're going to write that is g of x is equal to the absolute value of x minus 7 and then plus 11. Take this and move it down 9. So g of x is going to equal x minus 9, because we're moving down 9, it's on the outside. And that, which sounds a little bit funny because it's like, well, there's no inside, like what would I do for inside? Well, we can do that. If we wanted to move it left or right, we could have like an x minus 3 and then minus 9 on top of that, and then it would combine to be minus 12. It's kind of a strange situation when we're doing two things, because we're moving it left and then we're moving it right and then moving it down. Translate left 6 units and down 2 units. I want you to do this. You do. I like when I have you do something, and then that way, if you're wrong, it's okay. Just do it. Just try it. If it's wrong, we'll fix it, and I won't take off points if it's wrong. I just want you to try it. Same with on the last slide. Okay, please do those because those are valuable. So what we've done here is we just sort of laid out what we know about writing a function based on its parent function and whatever translations are coming. Here we're going to look at graphs, and we're going to have a couple of these to do before we're done. So the first thing is we've got this picture of the absolute value graph of wait, is this? Oh yeah, of the absolute value graph. Sorry, I was this f of x. So we've got this absolute value graph. This is the parent function here. The graph of f of x is shown on the same coordinate grid graph g of x. So we know that we're going to take the same picture and we are going to go to the right 2 spaces, and then we're going to go down 5 spaces. So basically what I want for you to do is recognize that we're going to go to the right 1, 2, and then down 1, 2, 3, 4, 5. And every one of these points is going to go over 2, down 5, over 2, down 5, over 2, down 5. And it's going to be the same picture, it's just moved over 2, down 5. All right? So we can sort of predict where all of these points are going to fall so that we can connect our dots and draw our graph. Sorry that this window is a little stretched on us. Right? These are like rectangles instead of squares, so it just looks a little funny. And then our vertex basically was at 0, 0, but now our vertex is at 2, negative 5, because it went 2 to the right, and then it went down 5. All right? That is how we would graph this if we know the graph of the parent function. And at this point now, you do know the graph of the parent function, and you don't need to use your grapher to graph the absolute value of x. But my hope is that you don't need a grapher to graph that g of x is equal to the absolute value of x minus 2 minus 5. That is the graph that we drew here. And now if you type in f of x, or y1 is equal to the absolute value of x, and y2 is going to be x, the absolute value of x minus 2 minus 5, you're going to get these two pictures. All right, you can check that with the calculator should you prefer. All right, this one looks a little bit funny, and I've been having you do the last one when we get a last example, but I'm going to do this one for you just because the graph is a little bit funky. Here we have closed circles on these points. This domain goes from -7 up to +6. But what we're going to do is take this weird function, whatever it is, and we're going to move it one left, and then 3 up. So from each one of these points, we can pick some points and then we can connect those dots if we would like to. We are going to go back 1, up 3, back 1, up 3, back 1, up 3, back 1, up 3, back 1, up 3. All of those dots are going to move. And now when we connect those dots, we will have a graph that is back 1 and up 3. You'll notice that I used the origin, the point from the origin on there. I didn't need to do that, but I wanted to. And now we have made this picture. Okay? Which is the same picture, it's just moved back 1, up 3. It's the same picture. All right. Hopefully now you feel confident to be able to use and apply transformations so you can graph their functions and write their equations.